Dr. Li, Chief Scientist at Nanode Battery Technology. He will introduce us the topic Beyond Lithium, Redesigning Sodium-Ion Architectures with Tin-Based Anodes with Streamlined Fabrication Techniques. Please welcome Dr. Li.
Sounds good. Okay, hello everyone. So thank you for having me today. My name is Jiankuan Li, and I'm currently the chief scientist of Nanode Battery Technologies. So in this presentation, I'm going to briefly talk about the technology that Nanode has developed for anode design, especially in sodium-ion batteries. Well, lithium-ion batteries still will maintain its domination. There are a few problems that need to be solved. For example, the safety risk, the volatile price of the lithium raw material, as well as the potential ecological issue of the caused by the nickel and cobalt mining. As one of the most promising beyond lithium-ion solutions, sodium-ion battery have become pretty popular in the recent years. Actually, there are a few major advantages of the sodium-ion battery. First of all, sodium is more than like 1,000 times more naturally abundant than lithium on the planet, which means that the overall material cost can be much reduced, especially after mass production. Sodium-ion battery also generally behave better fast charging and low temperature performance due to the relatively lower dissolution energy of the sodium ions and the lower viscosity of sodium-ion battery electrolyte. It also eliminates the use of the copper current lector, which means that the sodium-ion battery can be discharged to close to 0 volts, which is safer than lithium-ion. And since it can also exclude the use of nickel and cobalt elements, so it will also avoid the complex recycling process of these elements. So overall, sodium-ion battery is abundant and affordable alternatives to lithium-ion batteries. However, the biggest challenge of the current sodium battery is the low energy density, which limits this technology to applications that do not require high energy density. For example, the energy storage system. From the figure on the right-hand side, we can clearly see the sodium battery is not competitive at all in terms of the energy density, both gravimetric and volumetric. If we look at some detailed numbers here, for the watt hour per kilogram numbers, NMC has around 250 to 300. LFP is a little bit lower, but still can achieve 160 to 200. However, the sodium-ion battery can only have 130 to 160. Actually, this is already higher than average number. Many of the sodium battery only have around 100 to 120 watt hour per kilogram in this range. If we look at the volumetric energy density, the difference is more significant. The volumetric energy density of the sodium ion is only half of that of LFP and probably only 1/4 of that of NMC. So basically, sodium ion battery has lower gravimetric energy density, but at the same time, much lower volumetric energy density than the mainstream lithium ion batteries. To address this issue, much efforts have been made to improve the energy density of the current sodium-ion batteries. Apparently, compared to other components in the cell, the key is definitely from the both electrode, cathode and anode. As for the cathode element, we currently have three types of major options, which are all commercially viable, and they're actually way more focused on the cathode side compared to the anode side. And some of the influential companies in in the sodium ion battery industry also working on this area. As for the anode side, the only mass-produced option right now is still the hard carbon. However, there are a few problems. For example, it has relatively low specific capacity, only 300 milliampere per gram, and it has not been increased too much. The type density is also pretty low, which makes it difficult to build battery with high energy density, especially volumetric energy density. Uh, in addition to that, the quality also varies a lot depending on the different source, carbon source, and different fabrication method. As for other options, sodium metal is still very early and challenging. For the alloy anodes,